My voice is a little bit bad today, so hopefully it will survive the remainder of this talk, but I'm very thankful for this opportunity to speak here at PITP. Today I'll be talking about some more pedagogical stuff, but also some more recent applications about anyon condensation. So we'll start off with the algebraic theory of anyons, and then we'll develop an algebraic theory of anyon condensation. And this first application is more formal. It's just asking the question of, given a symmetry, how do we detect the anomalies? This is very actually related to Xiaogang's previous talk, but we will do it using the formalism of anyon condensation a bit more explicitly and also go through a few examples. There will be more references as we go on. And then the second application is more applied, I guess. And we will show how we can use anyon condensation to make some experimental predictions, even though it's a pretty formal tool. I should mention that there are many, many other applications of anyon condensation, more recently in dynamical codes, in quantum computing with gap boundaries, in many other contexts, but we'll just focus on these ones today. And for other references, these are some nice references that go through the more involved formalism and examples. Okay. To put everyone on the same footing, let's talk about the algebraic theory of anyons. And anyon theories describe gap phases of matter in 2+1 dimensions and also higher, but we're going to focus on 2+1 dimensions. And they, in the IR, they're described by spontaneous symmetry breaking phases of possibly non-invertible one-form symmetries. So for the beginning of this talk, I'm not going to consider any zero-form symmetries. And we're just going to consider the fundamental basics of the algebraic theory of the quasi-particle excitations of these gap phases of matter in 2+1D. To specify a particular phase of matter, or anyon theory, you need a few pieces of data about the quasi-particle excitations. So we can group them into 4 pieces of data. One piece of data are the anyon types. So this is a finite set of labels, and these label your quasi-particle excitations. So I can create an anyon A with its kind of conjugate A bar using a string operator from the ground state. The second piece of data are the fusion rules. I should mention that there always exists the vacuum label. The fusion rules tell you if I have 2 different anyons and I bring them close together, what does it look like? So if I have A fused with B, that can in general give me many different outcomes. And they're labeled by these integer, non-negative integer fusion coefficients and ABC. And pictorially, that just looks like this. Now, associated with these fusion coefficients, so there's a dimension of a vector space here, and the dimension of that vector space is given by this integer. Associated with these fusion coefficients, you can define a quantum dimension. So this is a dimension associated with this anyon. And the quantum dimension tells you how quickly the Hilbert space size grows as you add more and more of these anyons into your system. So for any anyon A in your system, there exists an A bar such that A fused with A bar gives 1 along with other stuff, possibly other stuff. And in abelian theories, this has a deterministic outcome, and all the D's are 1. But for non-abelian theories, generally you will have multiple fusion outcomes, and there will be some D that is greater than 1. And using these quantum dimensions, we can define a total quantum dimension of your theory as follows. This is overall the anyons in your theory. The third piece of data tells you how the anyons fuse and braid with each other. So this is F and R symbols. the F symbol won't be so important for today's talk. It's important kind of indirectly, but won't be so visible in today's talk. But it tells you if I fuse two anyons, and I try to move this, fuse them in the other direction, in what way are they related? And for abelian theories, this is just a phase, but for non-abelian theories, there's a non-trivial sum over F in general. The R symbol, which will be more relevant for today's talk, describes how the anyons braid with each other. So we have this diagram, and you have A and B, which might fuse to C, and this is related to the unbraided diagram by this R symbol here. And using the R symbol, so the F and R symbol have to satisfy some consistency equations, but if you can find solutions, you have a well-defined anyon theory. And using the R symbol and these quantum dimensions, we can compute a topological spin for each anyon, which will be quite important. So you can show that there's a topological spin So this diagram is if I take the vacuum and I create A and A bar, and I create A and A bar here, I exchange the A's and I reannihilate them. And this gives you the topological spin. It's an exercise for the reader to derive this relation. Okay, and then the final piece of data that we'll have is the chiral central charge. And so this quantity tells us basically the number of degrees of freedom along the edge of your theory. If you have a bosonic theory, then there's a nice relation between the chiral central charge and the algebraic data of the anyons that defines a chiral central charge mod 8. So it's this Gauss sum formula. And this works for bosonic theories because you can always stack an E8 state that doesn't have any anyons. Okay, so this defines our theory of anyons, and a very simple theory that we can write down a Hamiltonian whose ground state has excitations with these properties is the very familiar torque code. So as you all know, that Hamiltonian is given by this exactly solvable form. And on the square lattice, the AB term acts on the four edges surrounding a vertex, and the BP term acts on the four edges surrounding a plaquette. And we can compute the ground state of this Hamiltonian explicitly because it's exactly solvable. The ground state is some superposition of all the loop configurations. So it's some superposition. You choose a basis, say the sigma z basis, and the ground state is a superposition of all of these loop configurations. Now let's suppose that we perturb this Hamiltonian. So now let's add this small term. And as you can see, this term will excite two En excitations. So if I add this, apply this term here, for example, on this link here, that will excite this vertex and this vertex term. And clearly, as we take this g to infinity, so in the limit that g goes to infinity, the ground state will just be a completely polarized state. So we can see that as we tune this parameter g, we undergo a phase transition from this toric code phase, which realizes this anyon theory with E anyons and M anyons, which are bosons with non-trivial mutual braiding, into this completely trivial phase. And this completely trivial, we can actually draw an entire phase diagram. We can draw an entire phase diagram. And this is the celebrated Brodkin-Schenker phase diagram. I can add this GZ, and I can also add a GX. As I tune this GZ and I tune this GX, I will always arrive in a trivial confined phase. And we have this deconfined topologically ordered phase here. The transition that takes you from one phase to the other is known as an Anyon condensation transition. And in this particular case, we actually know all the critical properties also. This is described by an Ising star transition. The star comes from the fact that it's an Ising transition, but we've gauged the Z2 symmetry, so we only allow the Z2 even operators in the CF2. But the exponents and stuff, we know all the properties of this theory. So an Anyon condensation transition can take you from this deconfined phase and undergo a phase transition to a trivial phase. Yes? So GX is just some parameter that, GX is, I could also add like a, for example. Okay. As Meng talked about in his talk on Wednesday, when you want to go from one phase, a symmetry broken phase, to a symmetric phase, you do so by proliferating the defects of the symmetry, thereby symmetrizing with respect to the symmetry. So taking this as a spontaneously symmetry broken phase of a one-form symmetry, what we want to do to get from symmetry broken phase to symmetric phase is to proliferate the defects. And the way to do that is to, as he showed in his talk, you can write this very explicitly. If we start off in, say, a state in the ground state space of the Ising SSB phase, we can symmetrize with respect to this symmetry by proliferating the domain walls, which are the defects of the symmetry. So let's take this to if I sum over all of these domain wall configurations in some coherent superposition, you can clearly see that this just gives me the paramagnet state. So similarly, you can think of this Anyon condensation transition as we start off in our topologically ordered ground state. I'm not going to draw it, but this is representative. And then we're going to sum over all insertions of the Anyon. So I have my original state. I'll also sum over this state. And then that will be equal to this trivial paramagnet. So we symmetrize with respect to this one-form symmetry by summing over the insertions, proliferating the defects. And so you can think of this proliferation of the Anyon excitations as this mechanism for this condensation transition. Now, as you can see, there are certain things that you can't just condense anything, right? Because, for example, if these anyons have non-trivial braiding relations, then you'll have configurations in the sum that differ by braiding phases. And then those can cancel with each other. So if you want to be able to do this proliferation consistently, then you need additional constraints on what you're allowed to condense. And that is what we're going to talk about now. Maybe I can just push. Okay, so before I get into the details, I should also mention that the object that allows you to condense from this deconfined phase to the trivial phase is the same object that allows the torque code to have a gap boundary to the vacuum. And intuitively, you can think of this as the object that allows you to condense to the trivial phase is a non-anomalous one-form symmetry that you can gauge. And if you gauge this, you can get a defect between theory B post-gauging and theory A before gauging at a point in time. But you can also have a domain wall in space between A and B. And for most purposes, I will just take B to be the vacuum. So this object that allows you to, this object that you condense, that allows you to have a transition from this topological phase to a trivial phase, also allows you to have a gap boundary. And so this is why the theory of bulk phase transitions induced by Anyon condensation also allows you to define which kinds of topological phases admit gap boundaries. And then the kinds of those gap boundaries are useful, as Zhang said, for this symmetry TFT holographic principle kind of analysis. Yeah, so this will be like gauging, this will be at a particular, this will be like going through this phase transition here now. Yeah. Sorry, can you repeat that? The transition is continuous versus first order. Yeah. Does that affect the nature of the domain mode? So that's a good question. We don't really know the properties of this transition in general. We can define the properties of the domain walls, and we know those properties generally for any A and B. At least theoretically, one can compute those things. But dynamics is a difficult question that we don't really know anything about for more complicated phase transitions. Okay. What do you mean offsetting a change? Like, what's the defect impact? Yeah, so, okay. I'm just saying that the same object, which is this kind of Lagrangian algebra that allows you to do a bulk phase transition because you condense this thing when you tune a parameter past a critical point, is the same thing that allows you to define a gap boundary in space. Does the thing in time, I'm just imagining, okay, so this is kind of just a schematic. But what I mean to say is that you can also choose a particular point in time to gauge the theory in all of space, to gauge the symmetry. But this is a kind of, yeah, a schematic for that. Yeah. The boundary is gapped? Oh. So yeah, so we'll show that the thing that allows you to condense these consistently with each other allows for this boundary to be gapped. But what I really mean by when I say gap boundary is that there's like a definition of what operators can end at the boundary. To relate that to actually a physical energy gap is a non-trivial question and has been answered in certain cases. But there's a definition of gap boundary in the math literature of a certain like ability to end operators topologically at this defect. But yeah, energy gap and things like that has been proven, for example, Z2, but not in general. Okay. Okay. So in abelian theories, the problem simplifies a lot. In abelian theories, oops. what you're looking for that allows you to do this condensation is a subgroup of your anyons that have certain properties. So in abelian theories, you have a Lagrangian subgroup. And this is a subgroup of your anyons that have certain properties. So for example, one property is that it's closed under fusion. The second property is that for bosonic theories and for fermionic theories, we can modify the above. So fermionic theories, so for bosonic theories, there's an additional constraint that for every anyon, there's another anyon that detects it, so it has non-trivial braiding with it. For fermionic theories, we'll add in a transparent fermion that braids trivially with everything else. So this is for, there's subtleties, but we can talk about those, but this is for bosonic theories. So it's a closed subgroup of bosons. And you can show that these two properties together imply that any two anyons in your subgroup have trivial mutual braiding because our ABC, our BAC, and this is just one. If ABC are all bosons. And then the third property that we're going to want for a condensation to the vacuum is that for any B that's not in L, there exists an A in L such that R A B R B A is not equal to 1. So this is saying for any anyon that's not in my subgroup, it gets confined due to its braiding statistics with some guy in the subgroup. This is what we have in the abelian case, and we can work out some simple examples. So in the toric code, which is untwisted Z2 gauge theory, we have four anyon types. And this leads, because these are both bosons, this gives us two Lagrangian subgroups. So I can have one E and one M. And a slightly modified version of this, so double semyon, I have also, again, four anyons, like Xiaogang mentioned, twisted Z2 gauge theory. But in this case, there's only one boson. So I only have one Lagrangian subgroup. And you can study, you can also do abelian condensation in non-abelian theories, and that's also rather simple. I recommend Fiona's paper to go through that explicitly. For non-abelian anion condensation, it's a bit trickier. For non-abelian anion condensation, you need to have a consistent way to annihilate these string operators, these anions at the boundary. And so there are certain consistency equations. So there, the object that you actually have, oh, and by the way, I think this together also means that the size of your subgroup is given by the total quantum dimension. In general, you could also drop this condition. So you only condense some subgroup that's not Lagrangian. And in that case, the theory after you condense your subgroup will still be topological. It won't be completely trivial. And then that will be given by like this relation. For non-abelian theories, it's a bit trickier. In this case, you have to find some things that are similar to the F and R symbols. that allow you to consistently bring these anyons to the boundary and annihilate them. So in that case, you have something called a Lagrangian algebra. And this guy, you can write it as basically a composite, so a composite of many different anyons with integer coefficients. So these NAs are integer. And you can define a dimension of this composite object, which is sum over NADA. And in this case, you want this dimension to match with your total quantum dimension if you want condensation to trivial. Now, I'm not going to go into too many of the details, but basically there are additional symbols that you need to define for this theory to be able to show that you can consistently pull these anyons into the vacuum. So for example, suppose I take anyon A, bring it to the boundary. There's a vector space that's defined by NA. That's the dimension NA. These are into positive, non-negative integers. Similarly for B, there's a vector space. That's the condensation space. And I need to define some way to fuse it, to make it consistent with the fusion rules of the anyons. So there's an M symbol that needs to be consistent with the F and R symbols of your original topological order. For example, there's another relation of the M symbol with the R symbol of your original topological order that allows you to write this diagram. And this basically implies that RABC, RBAC equals 1 if A, B, and C all have non-zero coefficients. So this is kind of a non-abelian analog of this condition. Okay, so anyways, if you can find some object like this and find a consistent M symbol, that means that you have some object that allows you to do an anyon condensation. It defines a transition to the vacuum, and it also defines a gap boundary condition for this topological order. And the last piece of more abstract information is that every gap boundary of a topological order also defines a symmetry. And this is used in the symmetry TFT framework. So if you have a gap boundary, that means that you have some way of letting a subset of your anyons and come to the boundary and get annihilated. There are also confined anyons, and when the confined anyons, they can't have excitations in the bulk. So let's call this another confined anyon. Maybe I'll use a different color. It can't go into the bulk, and it's also not a zero energy, like I can't pull it into the boundary. So it becomes a low energy excitation near the boundary. And one can show that these low energy excitations form actually a fusion category, and that defines a symmetry in 1 plus 1D. So you can think of these low energy excitations as as defects of a symmetry. In the simple case of toric code, then this actually is the 1 plus 1D symmetry can actually be thought of as the world line of the confined anyon. More generally, it's not so simple to do this mapping from bulk anyon that's confined to boundary symmetry, but one can do it. So that means that every gap boundary leads to a corresponding symmetry, which may or may not be invertible. And I'll call this symmetry A, which is a 1 plus 1D, possibly non-invertible symmetry. Okay. So now that we have our definitions, we can go into the applications. Yeah.
We start at random with fusion category, and then we discuss this Lagrangian subgroup. So it's like a subset of these angles that now is a
So originally, yeah, so this is specifically in the case of abelian theories, if you want to condense abelian anyons. So for example, if you have an abelian topological order, your anyons form a group anyways, right? The fusion forms a group because there's a deterministic outcome. So then this is just a subgroup of that group. But then for more general non-abelian anyons where you have different fusion outcomes, then you need to use this more complicated guy. Yeah. Yeah, so this is a vector space similar to that fusion space there. This vector space is not one-dimensional if there are multiple ways to annihilate this anyon at the boundary. The intuition is that the anyon actually, if it's non-abelian, so if it's abelian, this will always be 1. But if the anyon is non-abelian, then there are additional degrees of freedom at the anyon. So for example, you have a gauge theory of a non-abelian group. There can be additional degrees of freedom that can't be detected by gauge invariant operators. However, when you bring them to the boundary, there are instances in which you can show that those additional degrees of freedom become physical at the boundary. So then there's a non-trivial vector space here. And so alpha labels like a state in that vector space, or that condensation space, that labels different ways to annihilate this anyon at the boundary. Okay. Yeah. Yeah, so this has a square root. So for example, if I have Z2 gauge theory, I have 4 anyon types. So square root of 4 is 2. Yeah. Uh-huh. Yeah, there are different ways to tune through this transition. There's naturally, as you said, for abelian, we just add the short string operators. For quantum double, there's a generalization of that. And then for our general non-abelian, it's probably very complicated. I don't know of a good source that tells you exactly how to do that, given this guy. Maybe there's a way to do that given another set of data that also defines a gap boundary, which is a module category. But I don't know of a source that gives it from this guy. Yeah. Not necessarily. So for example, in double Fibonacci, right, you condense 1 plus tau tau bar. Tau tau bar doesn't have. No, this is like a direct sum, but not really a direct sum. Yeah. Yeah. Yeah, these NAs are integers. Yeah, so for Fibonacci and Ising, it turns out that it's a lot simpler. You can show that, yeah, so yeah, that's good. We should do some example. Maybe I'll do it here. So for double Ising, double Fibonacci, those take a nice form because it's basically a theory with its stacked with its time reversal. And you can think of any gap boundary in these theories. So this is just like C with C bar, and it has a gap boundary to the vacuum. So now you can unfold the theory. So now it's just a domain wall between C and C, and there's always a transparent domain wall. And so that transparent domain wall is every anyon in A tunnels through and becomes the same guy in C. Nothing happens. In this kind of Lagrangian algebra picture, the anyon tunnels to the boundary and then it becomes a vacuum. But now when we unfold the picture, the anyon tunnels to the boundary and it becomes the same anyon because it's a domain wall between the theory and itself. And in this case, you can show that there's always a solution for a gap boundary because there's always a canonical transparent domain wall between C and C. So for example, if you take double Fibonacci, we can always write a sum. This is like we can always write a sum of each guy in here with its time reversal. And you can show that there's always a solution for such a gap boundary. Like all these equations will go through. So similarly, for double dicing, that is going to be something like this. And you can show that the dimensions of these guys are exactly the total quantum dimension of these theories. Does that answer the? Yeah, so that one doesn't have a condensable algebra. There's just not even a boson in that theory that you can possibly condense. So there's no solution to any of these equations. And that has a gapless boundary. You can also see it because it has a non-trivial chiral center charge. And non-trivial chiral center charge already tells you that there's no gap boundary. Okay.
So is there any way to find the dimension of the divergent substance is equal to the dimension?
Yeah, so there's this is related to, okay, so one derivation I know of this fact is that, as Xiaogang mentioned, you can construct a 1 plus 1D theory by this sandwich construction. So you have a dynamical boundary and a topological boundary. And so this is like gapped, topological, and this is, say, gapless. And I have my quasi 1D system here. And I can tune this to try to get a CFT. But that CFT will only be modular invariant if you look at the gapless boundary, but there are also operators that you include in this partition function that come from tunneling from the gapped side. And then you can show that what that implies is that if I construct a vector, if I construct an integer vector that's like n1 equals 1, and a1 and a2, if I construct an integer vector, then this integer vector has to satisfy a certain relation with the S and T matrices in order for this theory, CFT, to be modular invariant. So for example, let's call this n. That means that Sn equals n and Tn equals n. Now you can evaluate this matrix element by matrix element. You know the S matrix, the top, it will be like 1 over D, and this is all the quantum dimensions. So this is like 1, dA1, dA2, etc. And then you can show that in order to match this 1, 1 matrix element, then you get this guy. Maybe I erased it. You get this equation. So for example, when this is Lagrangian, then this is just 1. So this is 1. This guy? Yeah, that's this. Yeah. Okay. Okay, so in the interest of time, maybe I will just go to the second application because Xiaogang talked a lot about the first application. But I will just give a very quick example for the first application. The very quick example, Xiaogang already talked about like the high level picture. As I mentioned, every gap boundary gives rise to a symmetry. And now we can ask, is that symmetry anomalous, right? And so as he said, from any symmetry in 1 plus 1D, there's a machine that you can crank. So it gives you a 2 plus 1D topological order. That's the center. And this machine that you can crank, if you want to do it in a physics way, is you compute the string net model, which is described, that process is described here. So for any symmetry, you can get a topological order. And one defining feature of this topological order is that it has at least one gap boundary. And that gap boundary has exactly this symmetry. So let's call this gap boundary LE, which is like Dirichlet boundary conditions. And this gap boundary has a symmetry A. And the question of whether or not this symmetry is anomalous, as Xiaogao mentioned, is whether this topological order, which is well defined by this relation, admits a different gap boundary, defined by another Lagrangian algebra, Lm, such that they only intersect on the vacuum. And we can already see that this detects anomalies in the abelian cases. So as I mentioned, in untwisted Z2 gauge theory, you can show that this symmetry A is a Z2 symmetry that is anomaly-free. And you have two Lagrangian subgroups in that case. One is 1E, the other one is 1M. And they only intersect on the vacuum. And for the twisted Z2 gauge theory, that corresponds to an anomalous Z2 symmetry. There's only one Lagrangian subgroup, which is 1E. There's nothing you can do on this side to have something that intersects trivially. And what that means is that no matter what gap boundary you choose on this side, and I'm going to choose a gap boundary because we want to have a gapped 1 plus 1D theory when we shrink this direction. No matter what gap boundary you choose, there's always going to be some intersection. So there's always going to be some Anyon that can tunnel through. And what that means is when you shrink the theory, you get an effective 1 plus 1D theory that has a symmetry by construction because of this gap boundary. And now there's going to be a non-trivial order parameter because when you shrink the theory, this tunneling, Anyon tunneling operator, you can insert at zero energy cost. And it breaks non-trivially with the symmetry, and it gives you a non-zero value of your order parameter. So the reason why you want these guys to intersect trivially is such that in that case, you can show that there's no order parameter when you squeeze the system. So you can also use this to compute SPTs. For example, if I take Z2 times Z2 symmetry, and this is anomaly-free Z2 times Z2 symmetry, you can show that the Z of A in this case is untwisted Z2 times Z2 gauge theory. And the untwisted Z2 times Z2 gauge theory has the following anyons. And all of the guys that they generate. So now I have E1, which squares to 1, M1 that squares to 1, and I have all of these anyons in my theory. And you can show that there is a well-defined LE. In this case, I'll just use Lagrangian subgroup notation because it's abelian. But there's two LMs. And you can see that both of these intersect trivially with this guy. And this means that for Z2 times Z2 symmetry without any anomaly, there's a trivial state and then there's a cluster state. But you can do this with any generally non-invertible symmetry to detect the anomalies. There are many other ways to detect anomalies, but sometimes this way is a bit easier. Okay, so let's talk a bit about real systems and experiments for the second application. And you can use these kind of Anyon condensation to drive phase transitions. And a very important question for if you're working with an experimental system is usually you have access to some of the topological data, but you don't have access to all of it. So for example, in the quantum Hall effect, what you observe is that when you apply a magnetic field, you have a transverse current. So you have Jx is proportional to Ey with this proportionality constant that is quantized. So you have sigma xy equals nu over 2 pi, and this nu is our filling fraction. And in the phases and the nice thing is in a lot of these gap phases, if you put this at low enough temperature, you have the correct material, large enough magnetic field, you find gap phases at not only integers, but also nice fractions. So this guy is quantized. And when it's an integer, we have a nice explanation for what the theory should be, because we can write down the Hamiltonian in the presence of a magnetic field. We can show that electrons form Landau levels, and we know why there's a gap. But when this is a fraction, then that naive picture breaks down, because naively you would have a large degeneracy. You actually need interactions to get a theory that is gapped. But what people usually measure is they measure some magnetic field, and they find that there are various values of the magnetic field where you observe a gap phase. And then the question that you might ask is, you observe a gap phase at these different fractions, what is the topological order that you're realizing there? And as we will see shortly, this gap at a particular magnetic field defines different filling fractions. So you can get one piece of the topological data, which is the filling fraction, but there may be many, many topological orders that can be realized at any given filling fraction. But we can use this Anyon condensation framework to have sort of a hint to what might be a reasonable choice of those topological orders. So to discuss quantum Hall phases, we need to add U1 symmetry to the problem. So we have anyons in the presence of a U1 symmetry. And the interesting thing about anyons in the presence of a U1 symmetry is that they can have fractional charge. And the reason is, now I create my AA bar, and I act with my symmetry everywhere. And if this doesn't have any random charges lying around, then I can localize the symmetry action to its action near the anyons. And I can write U G acting on psi. The symmetry composes in the usual way. But I can decompose H and G to its local action near the anyons. So this means that I can write this as UA H, UA bar H, UA G, UA bar G, right? But that means that if I just look at near anyon A, these two operators only need to compose up to a phase that gets canceled by the phase with these two operators. So then we have UA H, UA G only needs to compose up to a phase. And one can show that if you want that, so for example, if I have U1 symmetry, I can write UA of pi rotation, UA for pi rotation is going to be some phase. But this phase, if you want it to be consistent and this phase should really just give me the charge of this A, right? Because I applied pi rotation twice, so this should give me the charge. And without loss of generality, you can show that this phase is given by the braiding of A with a particular abelian anyon. So if you braid with an abelian anyon, you just get a phase. And you can show that if you want these phases to be consistent with the fusion rules and properties of your anyons, then you can parameterize this 2 pi I QA by the braiding with a particular abelian anyon, which is called the Vizon. Okay, so this is how you can get anyons with fractional charge, right? Because generally the braiding with an anyon is not going to be 1. Now, this gives you a symmetry fractionalization pattern because each of the anyons can carry fractional quantum numbers. And from this, you can actually extract the filling fraction. To see what the filling fraction is, instead of writing this, this electric field, turning on this electric field, I can instead turn on a time-dependent flux. And you can show that this will induce potential. And then, according to the sigma xy, there's a current that goes towards the insertion of your flux. And then it's not too hard to show that in this notation, you get a charge accumulation in this region because of this current. And that charge accumulation is precisely the change in the flux times sigma xy. And so if I insert a 2 pi flux, then this is just nu. Now, if I take an anyon A and A bar, and I nucleate them and bring it around this 2 pi flux insertion, what I will accumulate is just a Harnav-Bump phase. So I should just get e to the 2 pi I QA. But we also know that this phase is what happens when we braid with a particular abelian anyon. So then I can equivalently say that I have a abelian anyon V at the center there because of this relation. So then we know that the charge accumulated at the 2 pi flux insertion is just QV. And so this is going to give you the relation that the spin of this particular abelian anyon is going to be square is e to the 2 pi I QV. Okay. So this is all the data basically that you need to define quantum Hall systems, fractional quantum Hall systems. And the simplest example of a fractional quantum Hall system is the nu equals 1/3 state. The nu equals 1/3 state has a very simple anyon theory. It's just given by abelian anyons. So it's generated by A. And the anyons are labeled by this integer n. The spin of A to the n is e to the 2 pi I n square over 6. And then the braiding phase, so is given by this expression. Now, if we choose, you can immediately see that A to the 3rd is going to be our transparent fermion because it braids trivially with everything. And the Vizon we can choose to be the generator of this theory. And that has spin 1/6, so it has nu equals 1/3. So theta A squared gives nu equals 1/3. This is basically the simplest possible theory you can write down that satisfies this filling fraction. So you might think that when you observe a gap at filling fraction 1/3, this is the anyon theory that describes that. But there are more complicated theories. So what people observe is that if you tune the magnetic field, then there's a gap at this filling. And there's also a nearby gap at 2/5. So then the question is, what is the topological order that has filling fraction 2/5 that is most likely to be realized here? And this is started this whole hierarchy construction that was initiated. The initial papers were Haldane and Halpern in like 1983 and 84, I think. The story of daughter states coming from parent states. So in this perspective, we can view this 2/5 state as a daughter state that comes from a very stable, large gap parent state, 1/3. And the derivations in the older and all the way until recently was using the wave function. So if I have a wave function or an explicit Lagrangian, I can consider what happens when I tune the magnetic field. If I tune the magnetic field to be slightly smaller, what I will do is I will nucleate quasi-particle excitations. And those quasi-particle excitations will tend to be the ones with the smallest charge. So in this theory, the anyons with the smallest charge, the smallest negative charge, which are their quasi-particles because they're electrons, is so minimal quasi-particle. That's A bar. Yeah. And so you can imagine nucleating a density of these quasi-particles, and the picture here is that they condense into their own Laughlin state. And then you can derive a 2/5 filling. The perspective that we took in this paper that allows us to do this algebraically without a wave function or a Lagrangian, and kind of more generalizes easily to non-abelian theories, is to view this as a condensation of bosons in the usual sense. In this example, we start off with this 1/3 state. And the idea is that I start off with a C, which is our 1/3 state, it's our parent state. And if I change the magnetic field by tuning it a little bit away from the original value, I can nucleate a new theory D, because I have some excess magnetic field. So in principle, I can get a new fractional quantum Hall state. And then you can undergo a phase transition driven by Anyon condensation. Maybe I'll call this A because it's not Lagrangian. Generally, this is not Lagrangian, so this is not the vacuum, but it's some other topological order. And it's given by the relations, as I mentioned earlier, that you can get the properties of this by looking at the relative dimension of this condensable algebra versus the total quantum dimensions here. So in this very simple example, what we want to do is we want to start off with the abelian cyclic Anyon theory. And we want to find a D because the magnetic field goes down. So we have a bar nucleate. And this guy wants to condense, but it can't because it's not a boson. So it needs to find an anion in D such that the bound state can condense. And this bound state, not only is it able to condense, but we want it to be charge 0, the global U1 charge 0, so that it doesn't take you to a superconducting state, because we want a fractional quantum Hall state at the end of the day. So there are two constraints. First is the fact that this guy binds with some guy in D to form something that can condense. And the second constraint is that we don't want it to have non-trivial charge. So let's work through this very simple example. We have this guy that we want to condense. A minus 1 has topological spin 1/6. Suppose that we stack with the simplest possible D. So we just take D to be described by U1 level M, Chern-Simons theory. And the spins are similar to here, except now instead of 6, I have a 2M in the denominator. So if I stack with D is U1 level M, then I have spins theta B to the L is equal to e to the 2 pi I L squared over 2M. So this is a very simple theory, so we can take this as our ansatz. There's other things that one can think about, but that's requires a longer discussion. And we want to condense something like A inverse B to the L. We want this to be a charge 0 boson, so we can condense it. That means that this guy must be an integer, so it's a boson. And then we also want so I'm going to choose the boson in this theory to be b to the v tilde. So we also want it to be charge 0. And you can show, now we can solve, this means that L squared is 1 over 9 m squared over v squared. And this implies that L squared is 6n minus 1 over 3m. We can put these equations together, solve for m, and we get m is equal to 3, 6n minus 1 v squared, and L 6n minus 1 v. The simplest possible theory is if we choose v equals 1, and this will give me m equals 15 and L equals 5. And you can check that this guy is a boson that's charge 0, it can condense. Now, what's the total filling fraction of this theory? Now the total boson is going to be BA times B, right? Because we chose B tilde equals 1. Okay. And so if you look at the spin of A, B, then that will give me nu equals 2/5, which is matches, and you can also compute the topological spins of the theory after you've condensed this condensable subgroup, et cetera, and you find that it matches with these results by Haldane-Halpern for this 2/5 state here. The more interesting thing is if you have non-abelian topological order. There it can really be a puzzle of what the topological order really is. And the poster child for that puzzle is the filling fraction 1/2 state. There, when you have nu equals 1/2 plus some integer, there are 3 candidate states that are most likely. So one is the Pfaffian. The second is the anti-Pfaffian. And the third is the pH-Pfaffian. These all have the same filling fraction, 1/2. They all have anyons of similar flavors. And they're all good candidates, and there's reasons for each of them. So then the question is, when I measure a gap, a filling fraction 1/2, which theory does the system realize? And one way that you might use as an indicator for which theory you realize is by measuring the nearby gap phases, or the daughter states, that can arise from this condensation picture. And the reason is that these different topological phases have the same filling fraction, but because they have different spins, they have slightly different daughter states. So if you can measure the daughter states, then that gives an indication to whether your system was Pfaffian, anti-Pfaffian, or pH-Pfaffian. So you can go through this calculation, and you work through the calculation. You can find maybe I'll just write it here, actually. There's a quasi-particle hierarchy from when you take the magnetic field to be a bit smaller than the original one, and a quasi-hole one where you increase the magnetic field a little bit. So here you find that the quasi-hole is 8/17 filling, which is close to 1/2, but a little bit away, so it's a daughter state. And then quasi-particle is at 7/13. Here you find the particle conjugate. So you find quasi-hole is at 9/17, and quasi-particle is at 6/13. And these two were originally already determined by Levin and Halpern back in 2009 using the wave function and manipulations on the wave function. But this guy doesn't really have a nice wave function that you can work with. But we can still try to apply our algebraic framework. And here we find might be not surprising that these are particle-hole conjugate because you start off with a particle-hole symmetric state. And it's actually quite interesting because unfortunately, well, I won't do the experiment justice, but basically in various experiments that measured this 1/2 state, they actually see these daughter states. So for example, and I'm just going to draw the data, but you can believe me, maybe, that people really observe gaps in some materials where you find a 1/2 here, and this is like 7/13, and this is 8/17. And there are 2 examples, and there are also more recent examples. Where you can see that there are gapped states at the filling fractions that match either with Pfaffian or anti-Pfaffian. There haven't been any that match with pH Pfaffian. And then you can say that some of these experiments have realized Pfaffian, some of them likely realize anti-Pfaffian because of the daughter states that have been computed. And you can try to measure other properties of these phases, like chiral central charge, braiding statistics, but those are very hard to measure in general. What is easy to access is magnetic field and an accurate measurement of magnetic field, which gives you an accurate measurement of the filling fraction. So this is, and I believe that there are other kinds of applications that can be done in this direction, where you can use these formal tools to find some things that you can predict. There are many other applications of Anyon condensation. So for example, as was mentioned, what are the critical properties of these transitions? We don't know many things about that. There's also other things. For example, I might have erased the M symbol that I drew earlier, but you can do quantum computation with F and R symbols to create gates. Are there nice ways to create gates with explicit gates with the M symbol as well? I think that perspective hasn't been fully developed. And there's many other applications beyond that as well. So hope that there is some work to do in the future.
I think the filling from one half there's a abelian 3-3-1 state. That's another probability.
Yeah.
So the outer state different filling from.
Yeah.
So this is not including is a 3-3-1 state. Yeah, that's
Yeah, that's true. Yeah.
Can we strictly exclude the other states based on this? Because it might be true that the nearby state is not related by condensation. It's a good argument, but is it a strict statement?
Yeah, I mean, strictly speaking, this is just a physical picture that may or may not be true. So for example, for abelian states, it turns out that in abelian states at the lowest Landau level, the Jane picture is much nicer and has more predictive power. In these cases, it's like indicative that these filling fractions are daughter states because you don't see, like if they were part of a Jane sequence, you would see other states, but you don't see those. But this is only like a piece of evidence. You can't say that this is proof that this was the Pfaffian or anti-Pfaffian or whatever. But related to Jane, which I forgot to mention, is that there's also all of these other kind of classical procedures for getting different fractional quantum Hall states like flux attachment and projective wave functions and things like that. And translating those to topological manipulations, I think, is also an interesting question.
Experiments were done in higher Landau levels.
So they're done in various Landau levels. Yeah. So in the zeroth, of course, nobody has really observed that. Yeah.
So in the first half of your talk, you focus on bosonic topological
Yeah.
order. So in the second half, some of the examples are fermionic.
Yeah.
Just wondering, like, if some of the rules would modify the way we deal with fermionic.
Yeah, so strictly speaking, there isn't like a nice, well-developed framework for fermionic topological orders. In this work, what you can do to formalize everything is take a minimal modular extension and then do the usual condensation and then show that it's independent of the extension. There's like multiple different ways to approach fermionic systems. We had to consider fermionic systems because fractional quantum Hall states are built out of fermions. But indeed, the kind of most rigorous way that I know to go about it is to use the modular extension. Yeah.
Very naive question. So the original degrees of freedom you had form the C cat, like the C part, right?
Yes.
What do you get the degrees of freedom that form the other anyons that you need to pair with to condense?
Yeah, so you can think of it as like a give and take where like there's an additional magnetic field and I can take a portion of these guys to like form my D topological order as well. As long as I keep the filling fraction of the original one the same and like, because there's a ratio of flux to electrons, right? Yeah.
The Tory code which you deformed it.
Yeah.
The definitions explicitly break the symmetries,
Yes.
all the symmetries that Xiaodan talked about, including one-time symmetry and everything. In the other picture that's been used, the Anyon condensation was kind of gauging a higher form symmetry.
Yes.
Or it's breaking. But in the Tory code that you discussed, there's no symmetry. So why do you use the same formulas?
Do you mean like with the perturbations or?
So you turn on.
Yeah. Yes. 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 Yes.
But these two things completely break the symmetry.
Yes.
So the last, after you turn them on,
Yes.
there's no symmetry.
Well, okay, so that's the subtlety is that there's a formula, there's a way to show by Hastings and Wen in 2000s that all along this deconfined phase, there are dressed string operators that have expectation value 1. So you can show that if you have a family of gap parent Hamiltonians, you have a family of gap ground states, and you also have a family of string operators. So then there are exact string operators that have expectation value 1 and have the same algebraic relations as your original string operators. They're just slightly dressed. But then in the thermodynamic limit, and they have the same algebraic relations, so you can use that formalism.
No, as long as you don't cross the transition, I
Yes.
understand why you effectively have an emergent one-form symmetry.
Yes.
But the transition has nothing to do with that. But on the other side, there's no symmetry. So on the other side of the transition, the symmetry is gone.
So
Even at long distance.
that's true. And then on the other side here, you also just have the vacuum, like the symmetry is gone. Is that sufficient, or do you want?
It's not, but it's yours with time.
Okay.
So let's take all the speakers of this wonderful week